Hello again, and welcome back for another riveting physics problem that we're going to do. Today we are going to do, or this time today, we are going to do problem 11, a rotating bicycle wheel. Okay, so basically we're given some information here, and we've got a bicycle wheel. We could draw the spokes out, happy little spokes. Right, I'm not as good as Bob Ross though, but happy little spokes going through there. And this thing's spinning, right? We're spinning around. Okay, and then at a certain point they say, okay, this will be the moment we start our frame of reference. Remember, physics is all about a frame of reference. What's our starting end? We're going to call this green line t equal to 0, and it's going to be right here, and it's going to continue to go round and around. And we're actually going to accelerate the bicycle wheel. And they're all in radians per second there. So you're like, oh, radians, come on, let's convert them. Let's not do it yet. Let's save ourselves some effort because it's not that bad. The units are playing nice. Let's just leave them in radians, okay? So the first part, when we pull our information out, we're given initial velocity. Ooh, I wanted something different than the orange I've already used. Okay, initial velocity, which we're going to call these W's, right? And we're given it as 2.87 radians per second. Now, what else are we given? We're given an angular acceleration. Look at this, which is our alpha, and that is 1.66 radians per second squared, and we're given after a certain amount of time. So our time is 1.86 seconds. See, it's right here. Okay, I know it's like we start a stopwatch at time equal to 0, which in our picture we said right here when the wheel marks that we have a chalk line or whatever you want to mark right here, and it's continuing to spin around. And after this many seconds, we have some questions. So we want to know, hey, what is W final or final velocity in our linear variables, if you want to relate the two. And we also want to know what is our displacement. All for this though, it's delta theta, so we're going to go through angles, right? So we want to know that too. And that's our two questions. So I'm actually going to solve the easier of the two parts first, which I'm going to solve part 2. So I'm going to do part 2 first, people. So if you have not attempted any of these problems by yourself, or if you have, even if you have, pause the video now and give this a try. I've laid it out. Just use your kinematics, your circular kinematics equations, and crank her out. Crank problem part 2 out and give it a try. Then, if you get it right or get it wrong, go ahead and hit unpause and see me do it here. Okay, then part 1 has a little trick, but it's really not bad. It's kind of delta theta, but it's got a twist at the end. So let's do this one first. We have V final equals V initial plus AT, which in our angular variables is WF equals WI plus alpha times T. And we know all these over here, so let's crank away. It is 2.87 plus, yep, I left units off. Bad, Hendo. Sorry, I'm just going to leave them off here. In a little bit of a rush. Haven't you ever been in a little bit of a rush before? You've done enough problems, you just want to get one more done. It's kind of addicting though. You get one more done, like, oh, I could get one more done. Anyways, we get this, and it's 5.98, ooh, not 989. 6-ish, and it's in radians per second. And so that's this one right here. Okay. Fortunately, I have now limited my space here. So this is part 2. So you're going to have to forgive me. I'll do the best I can. I'm going to carve out the best space I can here and see where I can work. Alright, so let's solve for theta, or which is delta x if you wish, so it's V initial t, or W initial t plus 1/2 AT squared. Okay, so I'm going to solve theta equals, or delta theta equals 2.87 times 1.86 plus 1/2, oh no, out of space, 1.66 times 1.86 squared. Sorry, I am truly sorry. That is an absolute disaster in there. So if you can't follow it anymore and you want me to redo it, you can send me an email or send me a post on the message board. But anyways, when you get this, I got 8.2097, and it's radians. So that's what we went through. So this thing went through 8.2097 radians, or 8.21 radians almost. So how far is, I mean, they want to know in relation to this, but every trip around we're back to square one, right? To me, the easiest thing to do would be to convert the radians to revolutions, and then it might make more sense. I'm going to call this 8.21 if you don't mind. In order to convert this to revolutions, there are 2 pi radians around per trip, per 1 revolution. So the radians cancel, and so you're basically multiplying by 1 and dividing by 2 pi. The radians cancel, and when we divide by 2 pi, make sure to put 2 pi in parentheses because your calculator will not understand you want to divide by the product of 2 pi. So make sure you put 2 pi in parentheses when you divide. And when I do this, I get 1.3066 revolutions. Now, to understand that, that's still not the answer. But 1 revolution, and what is the, so we want to, wherever this ends up, we want to know this. But after, if this is our final mark, final spot after that time right there, 1.86 seconds. Once trip around is 1 revolution, aren't we back to 0, square 1, the 0 theta displacement from the original mark? So 1 revolution, and it's like it doesn't exist. So we go 0.3066 revolutions past this. Okay, the answer is 0.3066 revolutions. Wonderful, yes it is. But our answer will not accept it in revolutions. You have to convert it. And if you multiply by 360, I'm not going to show that here because I'm running out of room. I guess I should show it here, but you turn it to degrees by multiplying by 360. And for me, I got 110.4 degrees. And that's how much further past, and those were our 2 answers, how much further past this went. So it went there, and then went another 110 degrees. So obviously this isn't right. The thing should be more out this way, but you get the picture. Thank you. Have a wonderful day.